Previous works have uncovered numerous parameters that shape how users perceive stimuli from ultrasonic mid-air haptic devices. These parameters include the number of focal points, command intensity, and drawing frequency, all directly affecting perceived intensity. However, these effects can only be universally applied to other devices by understanding the underlying physical output. Moreover, the question remains, is it the perceptual information stemming from spatial-temporal modulation parameters, the physical characteristics of the stimuli, or a combination of both that most influences perceived intensity? Here, we introduce a two-stage model that explores the effect of spatial-temporal modulation parameters on the physical stimuli delivered, thus affecting the perceived intensity. 3 studies were conducted to construct this model. The first study characterizes the effect of each spatial-temporal modulation parameter on the physical stimuli. This includes the nonlinear effect introduced by command intensity, the driving frequency effect introduced by drawing frequency, the power limit effect introduced by the number of focal points, and the temperature effect introduced by device heating. In the following 2 studies, the physical properties of the device in terms of pressure and force were extracted from the spatial-temporal modulation parameters and mapped to perceived intensity. We found that all physical properties strongly correlated with perceived intensity, and the pressure of the focal point affects perception more than force. The absolute pressure relative to the minimal perceivable threshold correlated most with the perceived intensity. We developed a perceived intensity predictor based on this physical property. It should also be noted that the minimal perceivable threshold changes with drawing frequency. We identified the optimal operating frequency range of 10 to 80 Hz and developed our model there. In addition, the number of focal points and drawing frequency affect perceived intensity with reduced influence. This highlights the importance of our 2-stage approach, which provides a more accurate estimate of the physical stimuli delivered and predicts perceived intensity more accurately than naive approaches. Finally, we provide the perceived intensity predictor based on drawing frequency, number of focal points, and the absolute pressure relative to the minimal perceivable threshold. Please see the paper for more details.